Good afternoon, everyone, and thank you for joining us for today's webinar. My name is Josh Vickers, and I will be your host. I'm with RTI International and the Forensic Technology Center of Excellence. Today's webinar is our first webinar in our Emerging Forensic Research series. We're doing this webinar on firearms and toolmark research. We do have two subject matter experts today. Our first will be Dr. Robert Maher. He is going to be doing his presentation on audio forensics of gunshot sounds. Dr. Maher is a professor of electrical and computer engineering at Montana State University. His research and teaching interests are in digital signal processing, with particular emphasis on applications in audio forensic analysis, digital music synthesis, and acoustics. He holds a Bachelor's of Science degree from Washington University in St. Louis and a Master's of Science degree from the University of Wisconsin in Madison. He also has a PhD from the University of Illinois, and they are all in electrical engineering. He previously served as a faculty member with the Department of Electrical Engineering at the University of Nebraska in Lincoln, as well as Vice President of Engineering for Euphonics, Inc. and 3Com US Robotics in Boulder, Colorado, and has also taught part-time at the University of Colorado in Boulder. Just our quick disclaimer, the opinions, findings, and conclusions or recommendations expressed in this presentation are those of the presenter and do not necessarily reflect those of the Department of Justice. Any products and manufacturers discussed are presented for informational purposes only and do not constitute product approval or endorsement by the U.S. Department of Justice. And now that we have got that out of the way, I would like to hand things over to our first presenter and subject matter expert, Dr. Rob Maher.
Hello, good day everybody, and Josh, thanks very much for the introduction. I'm very pleased to be here today to get this session off with a bang, so to speak, and talk a little bit about audio forensics of gunshot sounds. So I'm speaking from Bozeman, Montana, which is in southwest Montana, not far from Yellowstone National Park. And I'm at about 5,000 feet above sea level, or 1,500 meters or so, and it's 5 degrees below 0 Fahrenheit here. So I saw somebody from Ecuador on the list, so I suspect you're having a little bit warmer day where you're located. So let's get started. So audio forensics, what's this all about? So what I'm going to be talking about today are several different aspects of audio forensic analysis, so we're probably going to want to understand a little bit about what this topic of audio forensics is. So I'll say a few words of introduction about that. I'll also talk about the concepts of gunshot acoustics, which is a specific type of audio forensic analysis. And we've been doing some research over the last few years to understand more about gunshot sounds, and so we've had funding from the U.S. Department of Justice, National Institute of Justice, to make recordings of kind of a scientific quality of different firearms and understanding what type of information can be available there. So I am curious if any of you wouldn't mind typing in the chat box if you have confronted audio forensic analysis or audio forensic evidence in the kind of work that you do. Assuming that many of you are tuned in because you're interested in this, but if you could add a couple chat responses there, I'll take a look at that as we go along. Okay, so that's the quick introductory remarks. So what is audio forensics? What is this all about? So audio forensics is the forensic science, or the area of that has to do with analysis and evaluation of sound recordings. And these types of recordings nowadays are very common just because the increasing number of law enforcement officers who are wearing vest recorders, the likelihood in many cases that we will have situations that people have mobile phones or other devices making recordings, and certainly the number of surveillance systems that are available in public places and private businesses and nowadays residential locations is really increasing. So in the cases of audio forensics, there are really three major areas of concern, and I've listed them here. The first one is often authenticity, and this refers to whether or not a recording has been edited, either deliberately or inadvertently, that might change its character from what it's purported to be. Very often in audio forensic evidence, there's a need to maintain the chain of custody of that evidence, just like any other kind of evidence, and then also various techniques to ensure that that there has been no alteration in the process of handling that evidence. The second type of forensic concern that comes up in audio evidence is often enhancement. This refers to taking a recording that might have noise or distortion or poor microphone placement and then figuring out a way to enhance that so that the conversation is more intelligible, or the portion of the recording of interest for a jury or a court might be maintained in a little better quality, especially for people who are not accustomed to using this type of information. The third area, which is mostly what I will be talking about today, is the interpretation and documentation. Audio forensic evidence often is used to help address issues of a timeline, when things happened, what order different incidents happened. It's often used in the case of gunshot acoustics that I'll be talking about to address questions about who shot first, where they were located when the shots occurred, and other information that might help develop a way to handle conflicting reports by different individuals who were at a crime scene, different witnesses. So we do a lot of this sort of work, and then often this evidence does end up in court, so preparing documentation and example evidence is often quite important. So that's the general overview of audio forensics. If you are interested in this today, we will be talking more about some of these topics, and I recently actually wrote a book on this topic, and so if you're interested in finding out more about the general field and getting involved in this type of analysis, this book recently came out from Springer Publishing, so I invite you to check that out. So in gunshot analysis, specifically, there are a couple different types of reasons that we would be interested in gunshots. I'm noticing, looking at the chat here, that several of you are in jurisdictions that have a shot spotter system, which is a commercial system that's used to detect in real time gunshots that might occur in a community and then provide location information for law enforcement to go check out what might be the cause of that. Gunshot detection is important in the United States in many different areas. It's also important to the military, and there are military systems available that do sniper localization that help the soldiers know which direction a sniper might be located and where to seek cover to get out of the way of those shots. So that real-time tactical information is something that's quite relevant. What I'll be talking about today mostly is the forensic reconstruction aspect of this, which is using gunshot information that's been captured in a recording that of a dashboard camera or a 911 call center phone call or something like that. So it's after the fact, the information's been recorded, sometimes in multiple different sources, and so assessing the timeline, determining some facts about the shooter location and orientation, and often there's a question about firearm classification, what type of firearm was used to make those different types of sounds. So we'll be seeing several examples of that as we go along. Okay, so for gunshot characteristics, I think there are several things that are probably reasonably obvious. One is if you're near the firearm, the gunshot sound is very high amplitude. It's also very short in duration, and so the sound level is loud enough that the audibility is very apparent. In some cases, it's loud enough to be damaging to the hearing of those around, and so often in a shooting range, people will wear hearing protection and so forth. I think very often people are accustomed to hearing gunshots in movies and television and video games and so forth that have a very long reverberant tail. So it's sort of a with lasting several seconds. The sound of the muzzle blast, the bang of the gun, is actually only a couple milliseconds long. It's much more of a pop sound. And some of you may have encountered ear witness testimony in which people will report that they didn't think it was a gun that they heard. They thought it was firecrackers or some other thing that had this very, very short duration pop. And so, again, it's interesting that many people who are not around gunfire very often are sort of assuming that it's going to be the Hollywood version of that rather than the sounds that we actually hear. And we'll look at some examples of that here shortly. Gunshots are also quite directional. The sound of the gun is much louder in the direction the firearm is pointing and much quieter off to the side and behind. I think before I got involved in this research, I had assumed that the gunshot was sort of equally loud in all directions, and so no matter where you might be hearing the gun, it would sound equally loud, but it turns out that it's quite directional. So depending on which direction the gun is pointing with respect to the microphone, that will change the sound level quite a bit, and that can be quite noticeable in the recordings. And if the shooter is moving during a recording, that may also be noticed in the audio. So we can see a change in level, not due to a change in firearm, but due to a change in the orientation of the firearm, and that's important to remember. Another factor of gunshots that is quite common if the microphone is not right close to the shooting position is that there are going to be echoes and reverberation. Reverberation is a fancy word that we use to describe all of that kind of thunder quality, all of the echoes that kind of overlap each other after a while. Forensic recordings that I deal with generally are dominated by those echoes and reflections. And in some cases, it's actually important to be able to recognize those echoes and reflections because that may give information about the location and the orientation of the firearm at that shooting, which can be of forensic interest. So we have to deal with all of these characteristics when we're working with these gunshot sounds. If we are near the shooting position, the audio recording may actually have a variety of information that can be picked up. And so, for instance, there may be the mechanical action of the firearm. So that's the cocking mechanism, the positioning of ammunition. Other aspects of just manipulating the gun itself may actually have telltale sounds that turn up in the recording, and that can be of forensic interest to try to identify the firearm or any of its handling characteristics. Probably the most noticeable sound is the muzzle blast. That's the bang that we associate with gunfire and goes off as the shot has been taken. There's actually, in the case where the bullet that's being shot out of the gun is supersonic, meaning it's traveling faster than the speed of sound, we actually get a mini sonic boom. The bullet itself actually makes a noise as it travels through the air, and for certain types of firearms and certain ammunition, that shock wave of the bullet may actually be detectable. We can sometimes have surface vibration, which is the loud sound may cause nearby objects to vibrate or move, and that can lead to other sounds. We have the sound reflections that I mentioned. These would reflect off the ground and off the walls and buildings and whatever else might be in the vicinity. And the other issue that we often have are recording issues. So many times the sound of the gun is so loud that it overloads the microphone and the recording apparatus, so we get what is referred to as a clipped recording, so it exceeds the level that we can handle. And we also may have a situation where there is what's called a codec. So for instance, with a telephone call, if we have a mobile phone, there's actually a digital algorithm that is running on the phone that's trying to capture speech sounds. Gunshots don't sound like speech, of course, and so they may or may not actually be represented very well in that recording. And so we have to be aware of those issues when we're dealing with acoustical evidence that involves gunshots. As I mentioned, if we have a supersonic bullet, a supersonic projectile that leaves the muzzle of the gun traveling faster than the speed of sound, we actually get a shock wave, and this diagram here is showing some of the information that we might be able to glean from that shock wave. So we have what's called the Mach number, which is the relative speed of the bullet. That's V compared to the speed of the of sound at that location. The speed of sound varies a little bit with temperature, so we would need to know the temperature at which this occurred to be able to make some estimates. If the bullet is traveling along from left to right along this line here that I'm indicating, if the bullet is much, much faster than the speed of sound, like Mach 3 would be 3 times the speed of sound, the shock wave is actually propagating almost perpendicular to the direction the bullet is traveling. So you see that it's a very narrow cone that's trailing behind the bullet in that case. On the other hand, if the bullet is just barely faster than the speed of sound, so close to just above Mach 1, the cone or the shock wave is very broad and is more or less traveling in the same direction that the bullet's traveling. So depending on where our microphone might be located as this bullet passed by, we may have a different timing between the detection of the shock wave and the detection of the muzzle blast from the firearm. So that information can be important in an investigation to determine where that shot might have come from. So the supersonic bullets are sometimes encountered nowadays, especially if rifles are used in the in that firing. Okay. All right. So I'm showing a graph here. This graph has time along the horizontal axis. So this is time in milliseconds along here. And vertically, this is the amplitude or the loudness of the sound as a function of time. And I'm wondering if, looking at this graph of this situation, if you can tell me, looking at that, how many gunshots occurred that created this sound. So looking at that, does it look like there are 1, 2, 3, 4, 5, or 6 gunshots? Or does it look like there are more than that? I mean, if somebody asked you, based on this recording, which is what we're looking at here, how many gunshots were there, what answer would you give? Okay. And in fact, this is 2 different microphones. I'm labeling left and right, and this would be the trajectory of the bullet is traveling along this way. And this happened to be a supersonic bullet, and so what we're seeing in this is actually, first, the shock wave of the bullet that is going from the direction the bullet's going and arriving at the microphone. And I'm seeing a red line here, which is the arrival at the first microphone on the left of that shock wave. And then I'm seeing a yellow line, which is the arrival of that shock wave at this right microphone a little distance away. And the time difference between those is because the spacing and the speed of sound, it takes a while for that sound to get from one microphone to another. So in this experiment we did, this is depicting the case where we might have multiple microphones and would pick up these sounds. The other important thing to notice here is that there's a secondary shock wave arrival, and that is the reflection of this shock wave off the ground. So the sound from the bullet went directly to the microphones, and then we also had that sound going down, hitting the ground and reflecting up, and then arriving later at those microphones again. So it's the same shock wave, but we're getting 2 reports of that at the microphones. Then sometime later, we actually then have the arrival of the muzzle blast, or the bang of the gun, arrives here. It's arriving later in this case because the bullet is moving faster than the speed of sound, so it gets close to the microphone sooner than the bang of the gun. So we see that time lag between those events. And then we also have the reflection of the muzzle blast off the ground, so from the gun to that location. And so even in this single gunshot, we already see that it's a very complicated recording. And in this case, we only have a single reflection really off the ground, and you can imagine if we had a nearby wall or a car parked there or something else, we would end up with even a much more complicated recording than this very simple case that we have here. So it just is pointing out that maybe assuming that the recording would just have a single pop from the gun may be more complicated than that. Here's another picture. In this case, we have a handgun that's shooting a bullet that isn't traveling faster than the speed of sound. So in this case, we don't see any shock wave ahead of the muzzle blast of the gun, but we obviously do receive the main sound and then the reflection of that sound off the ground. So even with a handgun and a single shot, we're getting a relatively complicated recording, and that needs to be dealt with. So if we have a situation in which we have a crime scene that might have different microphones at different locations or different orientations, this is the same shot but viewed from 3 different positions surrounding that shooting location. And you can see we get a different signature in those 3 different recordings, even in a relatively simple case. So often law enforcement or detectives or attorneys in a forensic situation would like to think that there's a signature or a one signal that is represented from a particular firearm. But what we have to recognize in audio forensics is that there's actually quite a difference in the recording just depending on where the microphone is with respect to the gun. And so we have to keep that in mind as we go along. Now, for our research, what we're doing at the university is trying to understand several things. We want to know a little bit about the limitations of what we're going to actually be able to interpret from gunshot acoustical evidence. If we've made a recording, what are we going to be able to determine from that? So to do it, what we have come up with, it was a way to make very high quality recordings of gunshots under controlled conditions. So these would not be the situation that you would encounter in real forensic evidence, but what we want to say is, if you were able to make a really, really, really good recording, what kind of information could you glean from that? And then what we would want to do for the end of the research is to figure out, well, okay, how much of that really, really high quality recording information can be available in a more realistic forensic recording obtained with a vest camera or some other type of device. So this is the research that we've been conducting. So in order to do this, we want to understand more about the effects of the firearm. And so in particular, we want a recording system that can pick up the sound in all directions. So we've contrived a way with multiple microphones to record from out in front of the gun all the way around to the back. So the azimuth, that term is referring to the orientation with respect to the direction the gun is pointing. So 0 degrees is where the gun is pointing. 180 degrees would be exactly opposite that, behind the shooter. And so we want to know what the effect is around that. As we've seen, the reflections from the ground and from other objects make the recording very complicated. So we are going to do in our research what are called anechoic recordings. And anechoic means no echoes. So to do this, we're going to raise the shooting position and the microphones so that reflection from the ground is delayed sufficiently that we can record the whole bang of the gun before the first reflection arrives. So again, it's a contrived sort of laboratory type of situation. And we're also interested in repeatability, meaning if there are successive shots from the same firearm, how different are those shots? What is the variability from one particular cartridge to another shot from the gun, and understanding a little bit more about what expected variability there might be. So to do this, we've actually created a set of microphones mounted, and this is a plan view looking down on where the shooting position would be. We have a set of microphones located at various angles all the way around from the front to the back of that shooting position. And we have those microphones a little bit away, 3 meters away from where the muzzle of the gun is located, and that allows us to get enough level that we can get a good recording from that particular location. As I mentioned, we're also doing this where we raise the shooting position, raise the gun 3 meters off the ground, and then that way the direct sound going from the gun to the microphone arrives sufficiently before the first reflection off the ground that we can get a complete recording of that gunshot sound before it's overlapped with the reflection. So again, this is for the research purposes. To do this, we use some very specialized microphones. These are 1/8 inch diaphragm microphones that are able to handle a very high intensity signal. And then we're sampling these with a special recording system so we can get the recordings at about 500,000 samples per second. So that it's a very high speed multi-channel recording system that gives us a very wide range of frequency for this recording. So here's a picture out in our laboratory, which is a field outdoors, and you can kind of get an idea of how this is working. We have a tall platform ladder where the marksman will be located. We position the muzzle of the gun in the center here, and then each of these little microphones you can see mounted on stalks around this arc then are capturing the sound in all directions. So here's a picture when the recording is going on. You can see the marksman up on the ladder with the firearm, and then the computer recording system and all the knot of cabling down here is picking up that sound at of that particular firearm. We had each firearm fired 10 times, and so we have 10 recordings of each one of these. Here's with a rifle, and you get the idea of what's happening. So for our testing, we did this with 10 different firearms that were available. So we have some rifles and a shotgun, and then several handguns that were equipped with different ammunition to see what the effects would be. And here's an example of a 308 hunting rifle. This is microphone 1, which is the microphone right out in front of the gun. So the marksman is trying not to hit the microphone, but shooting pretty much straight ahead. And as you can see in the recording, we get this initial pop, which is due to the supersonic bullet from this particular firearm. So that's the shock wave. And then here is the bang of the gun. So this is the actual muzzle blast of the gun, and you can see it started here at about 3 milliseconds in this graph, and it's pretty much over by 6 milliseconds or so. There's a little energy after that. But it's, again, very short, just 3 milliseconds in the case of this rifle. And there's an extremely intense crack of that shock wave of the muzzle blast that's apparent. If we look at the recording from microphone 2, this was at 16 degree azimuth, so just slightly off axis, we get a very similar picture. We get the crack of the bullet, the shock wave, and then we get the gun itself, slightly lower amplitude than on axis, but still pretty strong. Continuing on, and we'll just jump ahead to microphone 4. This is the microphone at 49 degrees azimuth, so it's kind of diagonal from the shooting position. And you'll notice here we don't have the shock wave of the supersonic bullet anymore. And this is because at this angle, we're outside the angle of that shockwave cone from the bullet. So just because we don't see that supersonic shockwave doesn't necessarily mean that the bullet wasn't supersonic. It may mean that our microphone is just not in a position where we could pick up that sound. So that's an important factor to know. And if we go even to farther azimuths, 115 degrees, this is kind of back to the right of the shooting position. We can see that the amplitude has been reduced substantially. And if we go all the way to 180 degrees, this is the microphone that's located behind the shooter, much lower amplitude in that direction. Partly because the gun is directional, and then also the body of the marksman is attenuating some of the sound in that reverse direction. So this means we have to be a little careful about just assuming some details about the sound based on the level that we have observed. And here to summarize, we're getting kind of close to the end of the talk now. This is for a 308 rifle. These are 0, 16 degrees, 33 degrees, and so forth, increasing azimuth. And then these are the recordings of those muzzle blasts. And you can see for the microphones located close to the direction the gun is pointing, we actually are picking up those shock waves in that case. If we have, in this case, a 9mm Glock handgun doing the same recording, subsonic ammunition, so we don't see a shockwave in any of those recordings, and you notice we're getting a little different shape to the waveforms, so the recordings are slightly different compared to the rifle. We see a couple little more details in each of the shots, especially off to the side, and these are due to the various vents and the semi-automatic action of that handgun that produce other sounds that can be picked up and give a telltale representation of that particular firearm. To kind of compare things, this is on axis. This is out in front of the gun with several different firearms here, several pistols and several rifles. And you can see in this laboratory case, we're actually able to notice some pretty substantial characteristic differences between those different firearms on axis. So the hope is that if we could understand a little bit more about what would be picked up in a real recording, we'd have the ability to distinguish different guns and recognize and classify those different types of shots. So to conclude here, audio forensic evidence, as we've discussed and as you probably know in the agencies that you work for, is more commonly available nowadays. Many times there are surveillance systems or law enforcement wearing audio recording devices or electronic news gathering, or maybe people pulling out a cell phone at a crime scene and making recordings. So I think not only are we seeing more, but in the future I can't imagine that there'll be less audio forensic information. It seems very likely that this trend will continue. Audio forensic information may contain gunshot sounds, and that's, of course, what I've been talking about today, and something important to understand some of the characteristics of those sounds if we're going to make use of that information. So our research has been obtaining these reference recordings that can explain some of the complexity of firearm sound classification. And when I initially got into this work, I thought it would be very easy, and as time has gone on, I've got a little smarter to understand how complex these recordings can be based on all of the variables that go into that type of recording system. And we are continuing to do additional work, including testing a variety of common recording devices used by law enforcement agencies to understand how those devices are able to capture gunshot sounds and what sort of evidence might be available in those situations. So I want to thank you very much for your attention, and I know there'll be some time for questions later, so if you do have questions, please let me know. I do want to acknowledge the Forensic Technology Center of Excellence for putting this webinar together. I'm, of course, delighted to speak with you today. I want to acknowledge the National Institute of Justice for funding the research that we're doing on gunshot acoustics. And then I have several colleagues and students who have worked on this effort, and I want to acknowledge their contribution because this really does take a lot of work to collect and classify the data and make sense out of it. I provided a supplement with several links to some further information and some examples and different kinds of information, and I think that'll be made available to everybody participating in the webinar at the end. So you can look for that later on. And with that, I will turn things back over to our moderator.
All right. Thank you, Dr. Maher. We're going to go ahead and move into our next presenter. So our next presenter is going to be Dr. Rene Rodriguez, and he will be presenting on the restoration of defaced serial numbers using infrared thermal imaging. Dr. Rodriguez is a professor of chemistry at Idaho State University, where he has been an educator for more than 30 years. He has an extensive background in the use of lasers for chemical and material analysis, and his group has constructed and implemented instrumentation for this purpose. In particular, his group has previously constructed a coherent anti-Stokes Raman spectrophotometer. Currently, he is the co-PI on a grant funded by the National Institute of Justice regarding the construction and testing of an infrared thermal imaging system for the non-destructive recovery of serial numbers. The infrared lock-in thermography technique employs a pulsed high-resolution infrared camera, which is synchronized to a pulse laser heating source. Now, without any further ado, I would like to welcome our second presenter of the day, Dr. Renee Rodriguez.
Hello, Josh. Thank you very much for inviting me to be a speaker here. I would like to say I really enjoyed Rob's talk, and it's kind of interesting that both of us are out here in the Wild Wild West. I'm in Pocatello, Idaho, probably about 200 miles south, maybe a little bit southwest where Rob is, and we're actually probably about 150 miles from Yellowstone as well here in Pocatello, Idaho. I'm very pleased to be able to tell everyone about our research, which we've been doing towards the recovery of defaced serial numbers using a non-destructive method of infrared thermal imaging. And I have the good fortune to be the presenter today. Again, I have several people who I work with. We have PhD student David Unobe, Professor John Kalivas, Professor Andrew Sorensen, and also Lisa Lau, who is a research associate in our department. And we also have a few undergraduate students that have worked with us along the way as well, including currently Callie Castle is actually working with us. I want to kind of give you a general outline of the talk today, tell you a little bit about the research motivation for this investigation, the governing theory that's behind the idea of using thermal imaging, some of the objectives of the work, the methodology that we used, which has to do with these procedures of lock-in thermography, and also multivariate image analysis. Part of the idea was to be able to take infrared images of defaced serial numbers and using computer algorithms be able to take that information and be able to match the defaced serial numbers to a number library and then make an identification based upon the computer analysis. So, excuse me. I will also tell you about some of the results that we have. In particular, we've been looking at some of the actual real-world samples, including shotgun barrels, also some stainless steel forceps, which were actually laser engraved serial number rather than a stamped serial number. And also, we have been looking at a motorcycle vehicle identification number. And then I'll summarize what we've done here in the talk today. So to give you sort of the motivation for what we were doing, as you know, serial numbers are defaced in criminal activity. Often the degree that they're defaced to varies fairly widely. In some cases, someone will take a file to deface a particular part of a gun or perhaps something like a automobile engine. And the degree that it's defaced actually varies quite a bit. In particular, for instance, you can see in this particular image here that you have areas which have been defaced fairly well in terms of removing the number, but there's also a few numbers here that you can still see. And so the technique that we wanted to use would be technique which was non-destructive, so that it would also work over a wide variety of the different types of defacing that might be perceived, as well as to sort of be a complementary technique in the sense that it could be used first before some of the more common techniques such as chemical etching. I imagine there's quite a few of you out there who are involved in serial number recovery. Maybe you could text in and let us know who is involved in serial number recovery. But again, the idea would be to maybe use this technique to identify some of the, or try and restore the serial numbers first before going to the chemical etching method, which is a destructive technique, whereas this is not, would not be a destructive technique. So the governing theory behind this is that when you stamp a serial number into a piece of metal, there is a zone of plastic strain or a plastic deformation zone that results beneath the sample. So if we have our sample here, again, here's the stamp, and below that there's this zone of plastic deformation that results. And if we look at that zone, there are actually differences in the physical and chemical properties that result from this stamping in this plastic deformation zone. And chemical etching, which is probably the most used technique currently in law enforcement, uses the idea that there's a change in the chemical potential and the density of the material below that stamped region or below the laser engraved region, which again will result in a difference in the amount or the actually speed with which the material is etched away, and can then lead to identification of the number as the material is etched away. Again, a destructive technique. The idea of infrared thermography actually has to do with the difference in the thermal conductivity that is in this plastic deformation zone. And so what that means is if you can establish some sort of a thermal gradient across that zone, or in the region of the entire, let's say, number, then those regions in the plastic deformation zone, the heat conduction will be different than what it will be in other zones, other areas where there is not this plastic deformation. And so we can use then an infrared camera to be able to monitor this to see if we can actually look for differences in how the heat is moving. So basically this is, has to do with Fourier's law, which basically says that the heat conduction here, Q, is a function of the thermal conductivity, K, the thermal gradient, the change in the temperature is a function of the position, and also the area, the cross-sectional area that is being, that the heat is moving through. And so if there's a difference in the thermal conductivity between the plastic deformation zone and the surrounding areas, then we should be able to see that heat moving differently in the plastic deformed areas versus the regular undeformed areas. And again, that's the basis for what this technique should be able to do. So the overall methodology then is that we're going to do lab experiments using what's called lock-in thermography, which involves using a pulsed heating system to heat the sample and watch and create a temperature gradient across the sample. And then we're going to use an infrared camera to take several frames during a heating pulse to be able to collect thermal images that should contain information about the zones that are deformed, plastically deformed, and also other areas which are not. And hopefully we'll be able to see the differences between those two. Most often case, however, we're not able to see that very well, so we have to, and besides just doing the lab experiments, we actually have to do some multivariate image analysis. We have to actually take these thermal images and do some computer processing on them in order to be able to pull out the numbers from the thermal images. So the multivariate image analysis involves what might be termed image recovery. We're going to use what's called principal component analysis to come up with a series of orthogonal images. We'll talk more about this here in a minute, which actually may contain more information about the differences between the movement of the heat in the deformed areas versus the non-deformed areas. And once we do this, we would like to compare these images, which contain this information, to a number library so that we can compare with a computer the defaced images to a number library to actually do some sort of identification, hopefully more of an automated type comparison to come up with the best fit to identifying the number. And so to do this, we have to go through a few different steps. We have to first take the images of the defaced numbers and also the library and convert those into something that we can do a numerical comparison with, and that involves creating what are called Zernike moments or pseudo-Zernike moments. These are actually vectorized mathematical representations of the images. And then once we have that for both the images of the deformed areas as well as for the non-defaced areas, for the number libraries, then we can compare those two using what are called similarity merits. And then once we have the similarity merits, we can put those together using what are called fusion rules and then come up with a comparison and identify what that number is most likely to be, again, using a computer algorithm. So I'm going to tell you then about how the lock-in thermography is done, how the experiments are actually done. We use actually a laser. I guess the R got a little bit down here, but anyways, we use a laser to actually heat the sample. And this laser is a 5-watt argon ion laser. We put it first through a filter so that the profile of the laser beam is actually flat rather than a Gaussian type of a profile, so that it will get more uniform heating across the sample. And then we actually use a shutter to help us to pulse then the laser so that we can do pulsed heating of the sample. Because we want to create a thermal gradient in the sample, and we may want to do this repetitively so that we can actually minimize the background noise by essentially doing pulsed heating. So once it passes through this shutter, then it goes off of a series of prisms and then eventually onto the sample here, which is mounted below a FLIR 6700 series camera. And this is actually on a heated stage, which we keep the sample, again, the defaced number sample, a little bit higher temperature than the surrounding room's temperature. Usually we keep it at about 60 degrees or 60 or 70 degrees Celsius to sort of minimize the background from the room. And actually that moves it more into the best detection of the FLIR camera. So we're going to, as I said, pulse this at various repetition rates, and over the course of one particular pulse cycle, we can collect as many as 64 different thermal images. Typically we'll collect on the order of 15 or 30 type images over one pulse cycle, and then we can look at the movement of the heat through the sample to try and look for subtle differences in that and create then an image which can be compared to a numerical library image. So mathematically, what we have to do is create from this lock-in thermography, we create two other images, which in this case are an amplitude image and a phase image. The idea is the phase image should actually be able to get rid of a lot of just the environmental noise that is present in, let's say, the room, or slight fluctuations within the sample, or maybe I forgot to mention that these samples are all painted black, so the emissivity of the sample, we might have slight imperfections in the sample due to the fact that we didn't paint them all just quite the same. So this phase image actually allows those imperfections and the environmental noise to be minimized by essentially taking the ratio of the processed image that is collected here, this F. So again, we take, let's say, 15 different thermal images across one pulse cycle, and we may often do 15 cycles, and use all that, collect all those thermal images to create these phase images, which then should have minimal noise background and should allow us to make the comparisons that we want with the numerical libraries. Mention a little bit more about then the multivariate image analysis that is done. Again, most often just taking these images and looking at the raw images, you will not see an image of a number. It's only after you carry out this multivariate image analysis, the image recovery using principal component analysis, and then computerized number identification, that you actually can go and do the identifications of the numbers. The idea of principal component analysis is that you can the principal component analysis forms a set of orthogonal images from the original phase or amplitude images that are collected, and in projecting these input images into orthogonal directions, each principal component may capture even small variations of these phase and amplitude images, and these infinitesimal changes may reflect the heat conduction that's used to create the thermal images. The resulting principal components then are formed into score images of the same spatial dimensions as the original images, and these may provide a visual representation of this information that's retained in these respective principal components, which again are orthogonal to one another. And again, these orthogonal components, some of these components may contain this information about how the heat conducts differently in these plastic deformed regions. And so that's the whole idea, is once we form these score images using these the lock-in phase images or amplitude images, then we can compare those to a numerical library. First, we have to convert those into these Zernike, using Zernike moments or pseudo-Zernike moments. We extract the vectors from the score images that are then used to match them to the numbers in the library. I'm going to show you both Zernike moments and pseudo-Zernike moments just to kind of compare the two. We first started doing this technique with Zernike moments and then found that pseudo-Zernike moments actually is another way to do this, and they actually seem to work better in a few different cases, which I'll point out here in the examples that I'll show shortly. Once we do these calculations and form these Zernike moments, we then are able to we form Zernike moments of, again, both the score images that are derived from the experiment and also of the numerical library. And when we have these moments, then we can compare those two together mathematically or numerically using the computer. And we then can create what are called similarity measures, which means how similar then are these images to one another. And once we have created these similarity measures, then we can then fuse them together to come up with the best guess of what that number actually was using these fusion rules. And what we're going to see here is that always we're going to look, the fusion rules are designed, the similarity measures are designed such that the smallest value of the fusion rule will be the best fit and will tell us the best match between the score image and the number library image. So here's the number libraries that we've been using. These are just Microsoft Word fonts. Again, we have to take these Microsoft Word fonts and convert these into Zernike moments so that we can compare them directly to the numerical images that are derived from the experiment. The similarity measures that we use 15 different similarity measures. I'm not going to go through these in a lot of detail. Just note that they are all ways that we can numerically compare the score images that were derived from the thermal imaging to the numerical libraries that are essentially the Word fonts. And again, once we have these similarity measures calculated, then we can fuse them together using different fusion rules. And we actually use 14 different fusion rules. We sum both the raw merits and also the ranks of the merits. We can use a geometric mean or a harmonic mean. Anyways, what we do in the end is we combine these 14 fusion rules together to come up with a single consensus value via a summation or a majority vote of the ranks. The summation is essentially we're just going to sum all these similarity measures through the fusion rules together. And again, the minimal number will tell us what the best match is. And also, sometimes we can just come up with, or the other way to do this is to just rank them and then look for the lowest rank in terms of fusing these together to figure out what the best match is between the score image and the numerical library. So now it's at this point I'll show you some of the results that we've had to date. This is a sample that we obtained from Precision Forensics Testing Services, and basically you can see that it had a serial numbers stamped into it. The 6 here is a little bit, stamping wasn't all that great. You see that part of it seems to be missing. And then what we did was we took that and we gave it to a machinist, and the machinist took that and essentially defaced it by machining it to successively lower depths, and essentially then the number disappeared. And from the beginning of the 6 all the way down to the edge of the 6 was about 0.5 millimeters in terms of taking it off below the top of where the number disappeared. So we then collected the raw images, and this image over here is just what you would see if you looked at the raw image directly out of the camera. Again, it's hard to see anything there except maybe a little bit here at the top of the 6 might be present. And then what we do is we do principal component analysis using the 15 phase images that were collected over the 15 cycles. And we then come up with 15 score images. And here in these columns are the score images. These are labeled as principal component 1, principal component 2, principal component 3. These contain successively less of the information of the original image as you go further down. Now, if you look at these score images, how many of you can see that there actually looks like there might be a number 6 present in any of those images? I would argue that this particular image here at PC 13 looks somewhat like a 6 over here. If we blow this up over here on this side, you see that this does look somewhat like a 6. Now, in actually taking these score images and putting them into Zernike moments to compare with the numerical libraries, we actually use all of the score images. We don't just pick this particular score image and use it. We actually take all the score images for the comparison purposes. Also, the other numbers that were present, let's just remind ourselves what they were. There was a 2, a 5, and a 0 that were next to the 6. These are also show up in various score images. In the case of the 2, we see that it shows up at PC 11. The 5 shows up at PC 10, and actually the 0 shows up at PC 1. So we see that all these seem to show up. And so how then does the matching through the Zernike moments and the similarity measure and the fusion, how does that do in predicting what we would expect to see? Well, again, the idea here is once we have these score images, we create the feature vectors, and the number library also create the feature vectors using the Zernike or pseudo-Zernike moment. We then take those and combine those two and create similarity measures and fusion rules to come up with the overall ideas. So again, here's the score images of the number 6. Here's the numerical libraries that we are comparing to one another to decide what the best match is. So we're again going to use these fusion rule summations, a majority vote or a sum. If we look at this, remember the lowest number is going to tell us what the best match is. So along the top here, I put the numbers that we have that it could be is 0 through 9. And what we see is that the lowest value of the majority vote is a 1. And the lowest sum is also here is a 14. And it shows that this first number is actually a 6. This was using Zernike moments to convert the score images in the numerical libraries. If we use the pseudo-Zernike moments, we come up with similar type of a match. Notice that the difference between in the Zernike moments, the difference between the lowest and the next lowest is a little closer than in the case of the pseudo-Zernike moments. And also, in the pseudo-Zernike moments, we actually get a little bit different match here, as the second closest match is a 0, rather than in the case of the Zernike moments, it looks like a 5 is the second closest match. If we go to the number 2, then again, the best match for the number 2 is a number 2, and in the Zernike moment, using Zernike moments, if we use the pseudo-Zernike moments, we find also that to be the case as well. If we go then further to the number 5, we see that the number 5 has the best match as well to the numerical library. And again, if we use the Zernike or the pseudo-Zernike moments, the pseudo-Zernike seems to give us a little bit better match there than the Zernike moments in terms of the difference between the lowest value and the next lowest value here. Or, I'm sorry, that would be over here. And the 0, again, we find that this gives us also the best match here. The lowest value, the majority vote, and the summation is here at for a matching to the numerical library 0. All right, we also did other samples. We have a gun barrel, which we actually defaced ourselves. We took off a couple of numbers from the gun barrel. We have some laser engraved forceps. Again, there's a number here that's laser engraved into the forceps, which we defaced. Again, we painted it black when we heated it with the laser. And then we actually got a motorcycle from the Powell County Sheriff's Office here in Idaho that they wanted to see if we could identify the serial number so they could find out who its owner was. And so we took that as well. And the gun barrel, again, I'm showing over here on the side the best score image that we found. Again, this showed that on the gun barrel, the serial number was a 1, both in the Zernike and the pseudo-Zernike moment analysis. And the second number that we defaced was a number 2, and again, that was correctly identified here in terms of the analysis, lock-in thermography analysis followed by the multivariate analysis. For the laser engraved forceps, again, this is the PC that I'm showing. Score image over here that I'm showing was the score image that looked the best in terms of actually the 0 that we took off of the laser engraved forceps. Again, using the numerical analysis with the Zernike moments, we correctly matched this to be a 0 in both the majority vote and the sum in both the Zernike moments and pseudo-Zernike moments. And then the second number we took off was a 3, and again, that also gave us the best match here in terms of both the Zernike and pseudo-Zernike moments. Finally, the motorcycle vehicle identification number on the fork. We identified the numbers to be a 5. Again, that gave us the best match here in both the Zernike and pseudo-Zernike moments. The second number to be a 2 in the pseudo-Zernike and Zernike moment analysis. The third number to also be a 5. Again, that had the lowest values here in the majority vote and the summation in both Zernike and pseudo-Zernike. The next number was a 1, again, the lowest values here. And finally, maybe not finally, the next numbers were a 0, another 0, and this one gave us a 7. And then the final number that we got out of this analysis was a 4. Again, notice in this case, the Zernike moment analysis, there's actually another one for the sum that gave us also a 22 here. But in the pseudo-Zernike moment analysis, it actually showed this to be a 4 rather than a sort of a tie here between either a 4 or a 1. And we took this to, gave this serial number to the Powell County Sheriff's Office, and they matched it to a motorcycle that was stolen in Pocatello, and we're in the process of trying to get that motorcycle back to the owner of that motorcycle. I'm sorry, there's one more number here that is present, and that was a number 1. So in summary, we've sort of come up with or worked on this method that is a non-destructive method which could be complementary to the typical method of chemical etching. In many of the numbers cases that we've studied so far, the defaced numbers are correctly identified. The identification is fairly automatable The fusion allows a consensus of the number identification. We're working on expanding the library to include letters as well as numbers, and we're also developing a process using conformal prediction analysis to obtain confidence level and credibility of values for the matching of the numbers to the numerical library. I'd also like to thank the National Institute of Justice for funding this work. We have had a couple of grants through the National Institute of Justice here that are supporting this work. And again, I appreciate Josh and the Forensic Center of Excellence for inviting me to give
All
this
right,
talk
thank
today.
you so much, Dr. Rodriguez.
Be happy to answer
We
any
do have
questions
quite a
you
few
might have.
questions that have come in for both of our presenters, so we'll jump to Rob first. So Rob, the first question that came in was asked, how do silencers of the gun, on a gun, influence the audio?
Yeah, that's a very good question. If there's a silencer or suppressor used that will change the directional characteristic of the firearm, I think some people imagine that the silencer really makes the gun as silent as James Bond seems to be able to, but in general it's not anywhere near that much quieter. But it certainly will change the directional characteristic, and that can have some impact on trying to identify that firearm. So in the future, I'm hopeful that we'll have a chance to measure some of the suppressor products and see what change they would have on the different guns. But at this point, I don't have any data to share on that.
Rob, while we do, if you wouldn't mind, we might have some follow-up questions. So if you would put your email address there in the chat pod, and then Renee, you can do that after you answer your question. That way our audience members can have some good contact information for you if they do have some follow-up questions. So Renee, the next question is for you, and it was kind of touched on in your presentation, but they were asking if the method does work equally well with different types of metals that are used for serial numbers, such as stainless steel, metal plates, or aluminum alloy, and if so, did you find any types of material that proved more difficult than others?
Yeah, that's a great question. We have just started to do more analysis. We mostly have been looking at stainless steel. We started looking at some rolled steel recently and some aluminum as well. And certainly the thermal conductivity through those different metals is going to be a lot different. Aluminum is going to probably conduct very, very well. The steel doesn't conduct quite as well. And so we may actually have to change the pulse rate that we use. We actually try a few different pulse rates. But we may have to go to some much slower or much faster pulse rates depending upon what the metal is. So currently I don't have a lot of information about that, but
all right, Rob, next question coming back to you. What is the best way to overcome the recoil effect?
Okay, so I see Nancy's question here. I'm not sure what is meant by recoil effect. Is this the recoil effect of the firearm, that affects the trajectory, or if this is referring to reflections? So I guess if I could get some clarification on that, maybe from Nancy, I'd be able to address that
right after
better.
shooting.
Josh, do you have any idea what we're referring to there? Yeah, so from the acoustical standpoint, once the bullet has left the firearm, because the duration of that muzzle blast is so short, the muzzle blast sound is not affected much by the recoil of the firearm. However, the sounds of, if it's a semi-automatic firearm, the sounds of repositioning a new cartridge, ejecting the spent cartridge, and things like that will be noticeable, and that may have some effect on the overall sound of that gun. But as far as the direct sound of the muzzle blast itself,
Okay,
we
Renee,
wouldn't
this question's
expect there
coming
to
to
be a
you
change due to the
from Zoe
recoil.
asking, does your method work well on laser engraved serial numbers where there is much less plastic deformation?
Hi, Zoe. Yeah, actually, we've only tried one laser engraved serial number sample. That was the forceps that I mentioned. And in that particular study, it seemed to work fairly well. I think the numbers may not have been quite as, or the score images of some of the numbers may not have been quite as clear as they were in some of the stamp numbers, but so far, again, that's the only sample we've tried, and we were able to recover that serial
All right.
number.
Thank you, Dr. Rodriguez.
those
Before we move
forceps
to
that
our
we
next question,
actively
as
based
Julian
on.
has pointed out there in our chat pod, you will find both presentations available for download there in the file share pod at the bottom left-hand corner of your screen. So make sure you do download those before you leave. We also have the audio forensics reference that Dr. Maher was discussing, so you can download that as well. So the next question is coming to you, Rob, asking how does weather conditions such as raining, wind, pressure affect your analysis?
So the meteorological conditions can have an effect. If there is wind or rain or some other source of noise in the recording, and particularly wind can cause turbulence at the microphone, that can be something that can obliterate a lot of the sound or may have a just lowering the signal-to-noise ratio of what's being detected. The other effects of the meteorological conditions are that the speed of sound actually varies with temperature. And on cold days, the speed of sound is actually slower than on hot days. And that ordinarily doesn't affect our audition of what something sounds like. But if we're trying to make a measurement of a time delay, for instance, due to a sound reflection, or the time gap between echo and the sound itself, we have to have some estimate of that temperature because that will affect the relationship between the speed and the distance of that reflection. So often in a forensic investigation, if that sort of information is needed, there needs to be some estimate of what the temperature was at the location. The other effect of meteorological conditions has to do with distant sounds. So if you are some distance away from the sound source of a gunshot or something like that, the sound gets attenuated or absorbed as it travels through the air. A lot of the absorption depends on the humidity. And so depending on the relative humidity at the time of that shot, that might affect something about the audibility of that at some distance. So it's a good question. All of those things would need to be accounted
Rob,
for
just to follow up on
before
that,
making a forensic
Nancy was asking
interpretation
if
about the
atmospheric
circumstances.
pressure, possibly elevation, could have effect on it as well.
The speed of sound does not vary too much due to change in elevation. The response of the sound and the pressure disturbance and things like that might be affected, that could be detected in one of our kind of laboratory quality measurements, but we wouldn't expect too much of an effect on
Renee,
just a
next question
conventional
comes
audio
to you,
recording device.
asking how does surface texture affect the resulting images, such as a smooth filed surface compared to a rough scratched surface?
Yeah, that's a good question. If you have a very scratched surface, the sort of the parts that have been scratched where you have almost like an antenna, because the scratchings make a very sharp edge, then that actually makes the image very hot in that particular area. And so we actually do have to do a little bit of a surface prep before we are able to analyze these samples using the infrared camera. And what that means is we have to polish them, I think much like they're polished when before the chemical etching method is used. And then subsequent to that, we actually put a layer of either black paint or a layer of something like India ink over the top of that, using sort of a doctor blade technique to sort of minimize the scratchings and things that are there, because they will distort the images and are actually places where
Okay,
there's a lot
Rob,
of
next question's
emission
for
happening.
you. I'm asking for law enforcement agencies who use spotter or shot spotter type programs or software, is there a standard with which they set their microphones on poles?
So the shot spotter is referring to a commercial product and service that is available, I think, in North America, maybe in other countries. It's a proprietary system, meaning that the ShotSpotter company does not publish information about all the details of their product. So I don't know that I would be able to comment on if there was a standard for the microphone placement in that particular situation. ShotSpotter is designed to use multiple microphones to pick up sounds in the vicinity, and specifically trying to detect the characteristic sounds of a gunshot. The challenge for a system like that is that often where the gunshot takes place may not be in direct line of sight with the microphones, so the microphones may actually be picking up reflected sound or sound that's diffracting around an alley or a corner of a building, or having other kind of indirect paths to the microphone. So the difficulty there will be interpreting that, the precision of that type of a detection. So if this were being done out in a flat field somewhere, there would be one level of certainty, but if this is being done in an urban area or with buildings and reflecting surfaces around, it gets more complicated. So yeah, I don't know the direct answer, which is whether there's a standard, but that is a question that could be directed to ShotSpotter personnel
next
if
question,
there's a system in your area.
A comment for you, Renee, just saying that she was interested in more information about serial number recovery. Could you recommend any other resources?
I do have a few articles that I could recommend. I don't have those currently with me.
Okay, perfect. Yeah,
email
Nancy, if you just want to take down Dr. Rodriguez's email address, it is there in the chat pod. You might have to scroll up a little bit to find it. There we go. Julian just put it in the bottom for us. Thank you, Julian. So Dr. Rodriguez will pose this next question to you as well. What is the success rate for your defaced numbers that are often correctly identified?
Well, actually, part of this next grant that we have is to come up with some statistics regarding success rate. We're actually going to be working with the Utah State Police and the Idaho State Police crime labs to do some sort of blind testing to come up with the success rates. At this point, I would say just based upon the samples, of course, we know what the samples are, except with the one exception of the motorcycle VIN. However, the motorcycle VIN, I forgot to mention, there is actually also a number on the motor of the motorcycle which was stamped in the motor, and that was defaced as well, but it wasn't defaced very well. And so you could actually see a few of the numbers there. But to get back to the question, right now it would be hard for me to say exactly what our success rate is. I would say it's verging on about 50% at this point. But again, we're going to do some more testing here soon with cooperation with the help, actually. They've been very helpful of the Utah.
All right, Rob, next question is for you. Asking, are there any software programs available to assist in the analyzing of audio from a recording?
Yes, there are a variety of software programs available for this sort of work. I happen to use a product called Adobe Audition. So Adobe is, the company that makes Photoshop and handles Adobe Acrobat PDF files and so forth. They have an audio product called Audition. That's one that I happen to use. Other people use SoundForge. WavePad would be another one that's out there. There's a freeware or shareware product that you can use called Audacity, and that's available for download and has lots of good features if you're just wanting to kind of get a feel for what these recordings look like and how to handle them. There's some proprietary products for audio forensics work from several different companies. Cedar Technologies, Isotope is another one, and some of these companies will sell a license for kind of a workstation type of product. But yeah, so there are quite a few different choices that you might have for this type of work. What I would recommend is probably, if you're thinking to buy something, is talk to some other users who do forensics work and find out a good combination of features that
So we do have just a couple of minutes for a few last questions. Renee, they do come in for you, so I'll fire off the first couple quickly. So how much is the metal heated by the laser? Does the temperature change within the metal alter the plastic deformation and affect restoration by chemical etching?
Yeah, the temperature really doesn't change very much. What we see is a change of about, at most, 2 degrees in the metal during the pulse. The pulses are anywhere between something like maybe 20 seconds where the laser is actually hitting the sample and then 20 seconds off. And so over the course of the pulse, it may heat up as much as 2 degrees. Often it's much less than that, on the order of a half a degree.
Just asking if
what the second part, was there a second part to that?
Temperature had any kind of alteration on the plastic deformation and affect the restoration by chemical etching.
Right. Yeah, I don't, again, with that small of a temperature change in the metal, I don't think we're actually going to cause any changes in the plastic deformation zone. We really don't focus the laser down. It's actually broadened out so we get a nice uniform distribution across the serial numbers. So if we were focusing it down, yeah, we would certainly cause some changes. But
okay, last question. We have 2 questions. We'll kind of tie them together. Have you tried restoring serial numbers with alpha characters, and have you been able to restore any dot matrix type of serial numbers?
Yeah, we just started to look at the alphanumerics, and when we've expanded the library to include the alphabet, we do get more matches, for instance, between like a 0 and an O, or maybe a B and an 8. And so, yeah, we are just starting to look at that, and I think we're going to run into some extra problems there. With regard to the dot matrix, we really haven't even looked at that at all. I hadn't thought about doing that, but that's something that
All
we
right, thank you
probably
so
should
much.
be
That is all of our
looking
questions
at
we
as
have
well.
today. We are finishing right on time. So obviously the first thing we would like to do is to thank Dr. Rob Maher and Dr. Renee Rodriguez. You will find their email addresses there in the chat pod. So please make sure that you do take those down just in case you have any follow-up questions or would like to reach out to them for any additional reference materials. Before you leave, please make sure to check out the file share pod on the bottom left-hand corner of your screen. It does have both PDF versions of today's slide decks, and then it also has the audio forensic reference information that Dr. Maher was referencing. All you have to do is click on the title of the file and then click the download files button directly below that, and that will allow you to download that file. You will also see that Tyler is putting our social media outlets and links there in the chat pod. We do have our LinkedIn, Facebook, and Twitter accounts that are going constantly. So please make sure you start following us there in social media to stay up to date, as well as check out our website at www.forensiccoe.org, where you can find all of our no-cost offerings, webinars, reports, as well as our podcasts. We are in our new season of podcasts, so be sure to listen to our podcast and check us out there as well. You will find our customer satisfaction survey there in the middle of your screen. Simply click the word here. That will open up a new window for you and allow you to run through our customer satisfaction survey. Your feedback is always valuable information that we try to make sure we are delivering the best webinar experience for you, our audience, and the forensic community. Again, we would like to thank our subject matter experts for today, as well as everyone that attended today's webinar. We hope that you enjoyed the talks, and we hope you found the research as valuable as we did. We will be having another webinar tomorrow, so we hope everyone tunes into that as well. And again, this is the first webinar in our Emerging Forensic Research webinar series, so be sure to stay on the lookout for the next offerings in this series. Thank you so much for joining us today. We hope everyone has a great afternoon, and we will see you on our next webinar.